This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
The correct language to talk about continuity, mathematical language, that will allow you to actually compute things, is the language of limits. Okay? And historically, it came after continuity, and that's why I do it after. But if you look in the book, limits is done before. Okay? Because sometimes it's better, or each person has an opinion, it's better to present the development not in its historical order. But I like to present it in historical order, because then you can see the necessity for the idea of limits. Okay? So what's the idea for limits? Well, it seems, at least to me, clear that when you talk about continuity, what's important here is to look at the values very near where you are to see if it's one piece or two pieces, right? So the idea for limits is the following. Look, instead of looking at x equals 3, I'm going to look near x equals 3, but not at x equals 3. I am interested in what happens at x equals 3, but I'm not going to substitute x equals 3 there. I'm going to look to both sides of it, very close to it, and see what information I can gather. Okay? Here's how we write that. We want to find the limit of the function f of x when x is going to 3. Okay? This is code, all right? It's code. You have to understand a lot of stuff about what the code means. First, it means that x equals 3 is not allowed. You're not going to replace x by 3. Okay? You're going to replace values of x that are very close to 3, either bigger than 3 or smaller than 3. How close? As close as you can make. Okay? But I can make it really close. I can make 3.00001. That's close. And in fact, you can make it closer. You can make 3.000000000000000000001. And you can make closer. But I'm not going to say it. How close? Oh, you know, as close as you want. In the limit. I'm not going to explain that. There is a precise sense in which it can be done. You don't actually do it with a calculator. It's more of an abstract exercise. Okay? All right? But the important thing is, because you don't allow x to be 3, let's take a look at how this would work. Okay? Because you don't allow x to be 3, this is the limit when x goes to 3. I'm going to replace this expression here because x is not allowed to be 3, right? So I can replace. I can use this formula. X squared minus 9 on x minus 3. Can I simplify? Yes, because x is not allowed to be 3. And now, at this moment, something happens. At this moment, I am allowed to substitute x equals 3. Because I'm not dividing by 0. I mean, here I wasn't allowed because it would be like dividing by 0. But here it's OK. So this is 6. All right? You can think, oh, but is that what limits are? It's just a trick to allow you to divide and cancel. You could view it that way in practice. Okay? And how do I know I can substitute here, but I can't substitute there? Well, you can't substitute here because it would give you 0 divided by 0. And that's a no-no. Right? But you can substitute 0 here because it would give you 6. Is it that easy? Kind of, yeah. Okay? Visually, what happens? Visually, I am not allowed to use x equals 3, but I am allowed to use anybody who is near it. If you're near it, this guy is not very near, but I'm magnifying so you can see. Okay? If you're near it, what's the value of y? What's the value of f of x? Well, it's up here. And what happens if I slide this guy? Imagine it's a sliding guy, you can slide it. If I slide it towards 3, well, this guy slides down here, towards that empty gap. Okay? And the closest you can get to, the closer you get to 3, please, lights off. The closer you get to 3, the closer that gets to the empty gap. But never reach 3. Get close without reaching it. If you reach x equals 3, you go to b, right? I don't want to go to b. Okay? I want to get close to the gap. And this computation here, what it really is saying is that the gap is located at height 6. All right? That's what it is. And I did the limit from the left, I beg your pardon, from the right side. What if I had done it from the left side? If I had started, say, here, going up there, this is height 6. Okay? If I'm here, and approaching 3 from the left now, from the left, the values are increasing towards the gap. You're increasing towards 6. And from both sides, you go to 6. That's what it means to be one piece. Right? If it's really one piece, both sides have to go to the same spot. Okay? Compared to the one we had before. Bad marker, I'm sorry. Here's a better marker. Compared to the one we had before. Okay? Let's do the limit when x goes to 0 of f of x. What happens if you go, excuse me, what happens if you go from the right side that way? Well, from the right side, the formula you use is this one, which is x plus 1, remember? And x is going towards 0. Can you plug in x equals 0 in x plus 1? Can you plug in x equals 0 in the formula x plus 1? Yeah. Yeah, you can. Let me help you. It's this button here. Didn't work?
Oh, yeah, it worked, man.
You have to tell it carefully. Right? Okay. But what happens if you are on the left side? If you're on the left side, the formula for you is the formula x minus 1. And if you plug in x equals 0, which you can do, you get negative 1. And you're seeing that there's a gap from 1 to negative 1 in here. Okay? If there is a gap between what happens on the left and what happens on the right, if they don't coincide, you cannot have continuity. If there is no gap between what happens on the left and what happens on the right, you may have continuity. There's a chance. You can perhaps bridge the empty space in there if you need to. What does continuity mean in terms of limit? It means the following. This is a technical definition now. A function y equals f of x is continuous at a value x equal a if there's a lot written in there. Okay? So let me explain that to you. First thing that's in there, but it's not explicitly written, the value a is in the domain. Okay? For instance, x equals 0 is in the domain here. X equals 3 was in the domain there. X equal a has to be in the domain. How do I know? Because you're computing f of a. That's the first thing. The second thing that is in here, even though it's not said, is that this limit has to be the same from both left and right. You cannot have a gap like that. Having a gap like that means that from the left you have a limit, from the right you have a different limit, and there's no way to bridge the gap to be the same value that's in here. So they have to coincide from both sides. And finally, they have to coincide with the value of a function. In other words, looking at the picture that I very intelligently erased from here, but let me bring it back. That was the height b, right? And here is x equals 3 equal a. Okay? Is 3 in the range? Yes. Oh, goodness me. Hello. Hi. My name is George, and I'm here to talk about range. No, domain. Okay. X equals 3 is in the domain. So, check. Is there a limit when x goes to 3 of a function? In other words, when you approach from both sides, yes, and the limit is 6. That was the example we dealt with. Is it equal to the value b? B is f of a, right? If this number here is 6, it's continuous. If it's not 6, it's not continuous. So you have to have a limit from both sides going to the same number, and that number has to be the value f of a. If that happens, then it's continuous for that value of x. Okay? All right? That's what continuity is all about. To check if something is continuous, you need to be able to compute limits. So I'm going to give you 10, 15 minutes talk about computing limits. Okay? Mind you, you could spend 2 weeks computing limits. Let's do this example. Let's do that example. Let's do the other example. And you'll never do calculus. All right? We're not going to be doing that. We're only going to do the limits that we need in this course. Okay? And we don't need many. First thing, so rules for taking limits. C here is a constant. It's a number, 20 or 5, a fixed value. It doesn't change. It does not depend on x. Okay? It has a graph. I can draw a graph. You can imagine it's a constant function. Okay? You can imagine it's a constant function. Height c. And here is x equal a. So what happens if you go towards a without taking the value a? What happens to those heights? They're always equal to c, right? And so this limit is just c. The limit of a constant is the very number that you have. You don't do anything. Limits don't do anything to it. Okay? Well, if x is going towards a, what happens to x? It goes towards a. I mean, sometimes it's so simple that, right? Okay. What do you think happens? A squared. X is going to a, x squared goes to a squared. And I could fill out many more rules like this, but I want kind of one rule to rule them all, okay? I want to get one rule that will do it for all cases. Otherwise, you're going to be here forever writing rules. Okay? So let's see this. If you know that this limit here is a number L, and that limit there is a number B, if you know that, why did I choose B? Why did I choose L? A and B. L for limit and B for not limit. I don't know. A and B. Okay? Then, what do you think happens here? Okay? So if you know this guy is A and the other is B, if you add them, you're going to get A plus B. Okay? Let me tell you why I'm doing this. The goal here is to build more complicated stuff from simpler stuff. Okay? That's the goal. So if these two are simple, the sum is more complicated, right? So I can have an answer for the sum if I know each one individually. All right? You're building harder stuff from simpler stuff. That's what's going on here. What do you think that will give you? A times B. So you see why this is A squared. X goes to A, and X is squared is X times X. So you get A times A. It's that rule there. What's that? Just A by B. You probably mean divided by B. That's right, but there's a trap for you. Whenever you see a division, what's a trap? Don't divide by 0. So this is OK if B is not 0. If B is 0, that formula does not work, OK? Don't divide by 0. Dividing by 0 is like guaranteed to get the tax return people knocking on your door. Okay? You don't want it to happen. So let's take a look at what can you do with that. What is the limit when x goes to 1 of 5x squared plus 3x minus 2? Well, let's see. This rule here says that if I have a big sum, or a subtraction for that matter, it doesn't matter, I can put a plus or minus here. That's a plus or minus there. If I have a big sum or a big subtraction, all you need to do is to do each one separately. That's what it says. So this is the limit when x goes to 1 of 5x squared plus the limit when x goes to 1 of 3x minus the limit when x goes to 1 of 2. I have used this rule here. Okay? Now let's see. I'm going to write this in all detail because it's it's a bit of a pain, but there you go. This is a product. 5 times x squared, right? This rule here tells me that when I have a product, I can use the limit in each one of them. So this is the limit when x goes to 1 of 5 multiplied by the limit when x goes to 1 of x squared. Plus, same thing, limit when x goes to 1 of 3 times the limit when x goes to 1 of x minus Well, this is the limit of a constant, and the limit of a constant is the constant itself. So I'm not going to be writing limit anymore. I'm just going to write 2. You quickly realize that this is an absolute pain to write in every detail, right? You promise me you'll never do that in an exam or a quiz, because I don't want to mark it. Okay? I want you to know it and operate correctly with it, but it's the last time you're going to do anything like that, okay? Promise? Thank you. So every time you have a constant, it's just a number itself. So this is, oh wow, 5 times the limit when x goes to 1 of x squared. How much is that? 1. Plus 3 times 1 minus 2. And all of a sudden, this very last line I wrote has no limits. So just do it. It's 5 plus 3 minus 2, 6. 6 is the answer to everything today. Okay? Oh, but George, this was a polynomial. Well, polynomials are important, right? Question for you. Is this polynomial here continuous when x is equal to 1? Why? It is correct. You're right. Yes, it is. Why?
Because x is not equal to 0.
Not because x is not equal to 0. The definition of continuity is compute the limit, 6. Now, check that against the value f of 1. F is this, right? This is f. In other words, plug in x equal 1 here. What do you get? 5 plus 3 minus 2. You get 6. Yes! Okay, so it is continuous. In fact, you can argue the following. You can argue the following. And now I'm going to say one of these things that are very deep, okay? Very deep. When Descartes put equations into geometry, he gave you a way of eliminating the picture, working only with the equations. Okay? This computation here is a way to verify if something is continuous without having to draw the picture. How did I tell you about continuity? I say, draw the picture and see if it splits into 2 bits. Are you going to be drawing the picture every day? Of course not. Nobody draws a picture. You need an alternative way, and that's why algebra is so useful, because it gives you a way of concluding things without drawing the picture. Drawing the picture is a pain. All right? And so you can conclude continuity or discontinuity, if that's the case, without having to draw a picture by doing a calculation like that. Got it? All right. George, I hear you say, all very well and fine, but what happens if b is 0? Remember I said you can spend 2 weeks talking about limits? It's that case. The case when b is 0 is so interesting, I'm not going to say hard, but interesting, that you can spend a long time talking about it. And in fact, it's the only interesting case, because every other case, you know how to do. It's written here. Okay? So I'm going to give you one example of that. Now I'm going to give you 2 examples of that, because I've already given you one. Okay? And I'm going to just repeat that one. Now, whenever you see something like that, what you want to do is plug in the value 3. You want to plug in the value a, okay? That's what you want to do. All right? But you can't, because you get 0 divided by 0. You're divided by 0, can't use the formula. Because I want to use the formula, right? That's what I want to do. It's a formula about quotient, one divided by the other, but you can't. In a situation like that, in practice, what you have to do is find a way to simplify that so that the 0 is not showing in the denominator anymore. All right? As simple as that. That's what you need to do. So in here, we've done it already. These guys cancel. Why can you cancel? Because it's a limit. X is not 3, you can cancel. Okay? So this is the same thing as the limit. When x goes to 3 of x plus 3, now you can use the rules that we had before. Okay? And I'm going to do it one more time for old time's sake. This is the limit when x goes to 3 of x plus the limit when x goes to 3 of 3. So this is 3 plus 3, 6. Okay? But George, this was easy to simplify. What if you have something harder? Look, the truth is, that's on record, eh? The truth is, if you have something harder, really, really harder, then it's harder. Harder to the point that you can't do it, harder to the point that nobody of us here can do it. Okay? Limits can be an absolute pain. I'm not lying to you. George, will you give me a hard one in the exam? No, because I passed my sanity certificate. I'm not crazy. Okay? Anyway, so you won't have anything impossible in a quiz or exam. Having said that, there are some that are hard and you can still do if you know the right trick. For example, so let's take a look at that. X is going to 0. It's a fraction. So it's of the type f divided by g. Okay? Take a look at the denominator. The denominator is x. X is going to 0. So the denominator is going to a value that is 0. B is 0. You cannot use this formula. All right? All right. Now take a look at the numerator. The numerator is going to what? What happens if x goes to 0? This goes to, just guess, square root of 0 plus 1, which is 1. So it's going to 1 minus 1. 1 minus 1 is 0. So this limit here is 0 divided by 0. 0 divided by 0, let me tell you right now, can be anything. Okay? Can be anything. This could be 5, the answer to that. It could be 2. It could be a half. It could be 20. And you don't know until you try. Okay? How? Try how? Well, you need to come up with a trick to make this x disappear from the denominator. That's what you need, okay? The trick here is the following. I'm going to multiply and divide by the same quantity. Which quantity? I'm going to take it out of my pocket. It turns out I have quantities in my pocket. So I'm going to take this quantity out of my pocket here. I carry quantities in my pocket. Yeah. And the quantity is this. Okay? George, why did you choose that quantity? Because I already knew the answer beforehand? Is that okay? But not really. After you see it solved, you realize why I chose it, okay? Look at the numerator. Don't look at the denominator now. Look at the numerator. Let's carry out the product of this times that. Let's carry out the product of this times that. I don't know how you guys do it, but I do it slowly. Multiply those. What do you get? X plus 1. This multiplied by that is x plus 1. This multiplied by 1 is this. So I've done those. Now I'm going to do this. Which will give me that. And finally, I'm going to do this product here, which gives me that. You realize that these two cancel out. I am left with x plus 1 minus 1. I'm left with x. And lo and behold, remember what I said? You want to make the x cancel? The x will cancel. George, is it always possible to do that? Yes. As long as you have a 0 divided by 0, it always works. It may be tricky to find the correct thing to multiply, but it's there waiting for you. On the tutorial exercises on Thursday, we'll do more, okay? We'll do more. Now cancel the x's. Can you cancel the x's? Yes, because x is not 0. It's a limit, right? So you can cancel. Now let's take a look. Can you plug in x equals 0 in that expression? Yes, because you're not dividing by 0. You're not doing any of the forbidden things of mathematics. Okay? You're not eating the apple. Sorry for the religious image there, but okay? So, what you get? 1 divided by 1 plus square root of 2 Oh, sorry. No. Beg your pardon. I substituted x by 1, not by 0. Square root of 1 plus 1, which is 1 divided by 2, 1/2. And now, if you could see that it was 1/2 from here, congratulations. But I couldn't. I knew it was 1/2 because I've done this before I came to class. But okay. So let's recap here. We're almost done. We have rules for computing limits. Okay? That allow us to sum limits we already know, to subtract limits we already know, to multiply limits we already know, and to divide limits we already know, provided you're not dividing by 0. Okay? What happens if you are dividing by 0? Well, if you are dividing by 0, welcome to the zoo. Okay? Because there are so many different animals in the zoo, you can spend quite some time visiting the zoo. There are two things to remember, though. If it is 0 divided by 0, there is going to be a trick to see you through. If it's not 0 divided by 0, I'm going to give you an example right now. And it goes like this. It's simpler. It's simpler. It's simpler. Beep, 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 beep. What did I do with my... there. Okay? X is going to 0. This is going to 1 divided by 0. So we cannot use that formula that was here. It's not 0 divided by 0. It's 1 divided by 0. So we cannot simplify either. All right? 0 divided by 0, you can hope to simplify. 1 divided by 0, no. So what do you do? Well, let me show you what the graph of 1 divided by x looks like. It looks like this. If x is positive, you get positive values. If x is very, very, very large, it gets smaller. X is 10 is 1 on 10. X is 100 is 1 on 100. Okay? And if x is very, very small, it gets bigger and bigger. If x is very small, 0.1, 1 on x is 10. If x is even smaller, 0.01, 1 on x is 100. So as x gets smaller and smaller, you get bigger and bigger towards infinity. Okay? So if you're coming towards x, but positive, your y values are going larger and larger and larger to infinity. Likewise with x negative. If you're going towards 0 on the negative, the values of y are going to negative infinity. Okay? So this guy here is plus infinity if x is positive, and negative infinity if x is negative. Now, this is horrible mathematics. You should never write it like that, okay? Because x is not positive. There's a limit going on. Okay? What I mean is if you're doing the limit on the right and if you're doing the limit on the left. Okay? There's special notation for that. Can you stand more notation in the last 5 minutes of class? I hope so. Okay? So here's the notation. The limit when x goes to 0. On the right, take a look. On the right of 1 on x. Now this is saying that x is positive. That's the notation for positive x. And that guy is plus infinity. And the limit. When x goes to 0, but from the left side, there's a negative sign there. This is negative infinity. Okay? So it depends if you're on one side or the other. It's a new dance move. Okay? You go to the disco, the dance club, you know, and you start like this. You see people are going to look at you funny. Limit, when x goes to 0, of 1 divided by x squared. Now, you notice that because the x is squared, negatives became positives, right? So it doesn't matter if you go from the right or from the left, you get the same answer in the end. Okay? Happy with that? The graph of this function here is like that. Both sides going to infinity. Notice the following. This function is even. Symmetry here. So if you go from the left or from the right, you're going to get the same. This function is odd. So if you go from the left and you go from the right, you do get different things. And what do you get? Plus infinity. In this case here, if you want to be absolutely technically precise, the limit doesn't exist because for the limit to exist, it needs to be the same from both sides. Okay? On Thursday, we meet at 9 a.m. Now, who is going to be asleep? I'm going to be here at 9 a.m., and I really hope you are here too, because there's nothing that brings a smile to my lips as arriving at 9 a.m. and not seeing you here. Okay? So I hope I will see you here at 9 a.m., and then we'll do exercises from the book, answer questions, practice a lot. By the way, you know that there are tutorial quizzes, right? They are not this week. They start next week. We're going to have 2 tutorial quizzes during the first 15 minutes of a tutorial, but not this week. We're going to wait until you're in the swing of things and you've done some practice exercises and stuff like that before we start, all right? Okay, well, I'll see you Thursday. Cheers, thank you.